short homework assignment up. It's due tomorrow. It's only 4 problems, which is the stuff ostensibly that we tested over on Wednesday. We'll see how far we get today. And I'll let you know that information. But if we're having anything else. But basically, we're talking about the phenomenon of wave interference. And a couple things I want to subcontract out my graphics. Yeah, this is great. I just sort of discovered this picture this morning while I was helping someone out. But it's not a picture, it's a video. Let's see where we get to. Actually, I don't care about the video. Alright, well. Alright, this is the picture I'm looking for. Let me see if you can see that. Right, so this is diffraction in water waves. So over here on the side of this inlet, you have waterways which are coming in more or less in a straight line, right? When we were drawing the straight lines for waterways, like the graphic I drew on the board last time looks something like this, right? And I said to picture those as wave fronts. I don't know what the heck is a wave front, right? Well, you can picture like the crest of a water wave as it's propagating through the ocean. That's what we're representing when we draw these vertical lines. And it's hard to see the waves on the other side of this, but notice what happens after they go through this opening. They have fundamentally changed shape, right? They've curved around. They diffracted around these barriers. Remember, diffraction is the bending of a wave due to something being in its way. It's in the same medium. Refraction is the bending of waves as they move to different media, but diffraction occurs in the same medium. And it's because it's bending around barriers. I also found this picture, which I absolutely love. Let's see if I can get this a little bigger. Or not. Alright. Fine. We'll go with this. You can see it. Alright? This is a picture sort of, not exactly from the side, but from an angle of 2 wave sources as the waves overlap. So you have something causing a wave here. It's probably something moving up and down and underneath the water. This is a wave tank. You have another source here. You can imagine dropping a pebble in a pond and dropping another pebble pond and the waves ripple out. If you do it rhythmically, you get a pattern that looks like this. And that's what's happening here. There's something producing these waves right here in the center. But look what happens when the waves interfere, right? Where these waves are crossing, and what you see, this is illuminated from the side so that you can see the peaks of the wave. When they're crossing here, you get this section like right here, where you have total constructive interference of the waves. They're building up to make a wave bigger than either, or I should say, to make a peak bigger than either of the 2 constituent waves. And then here, you can't see it in that really dark spot. That is also constructive interference. It's just on the other side. Right, you have 2 troughs lining up to produce this sort of depression. And then somewhere in between there, you have total destructive interference, somewhere in between the middle and the side, like right there. Total destructive interference where the wave is actually just canceled. So what's happening, if we allow these 2 waves to propagate out, they're just going to interfere with each other, and then once they leave the region where the other wave is propagating, they'll just look like a normal wave. But if I were to put some sort of barrier right here, like just some sort of wall, and I could call it a detector, but what that would mean would just be a wall that you can look and see where the watermarks are. Well, if the wall doesn't move, there will be sections where I get total constructive interference hitting the wall, and that will look like a high watermark. I will get sections where I get total destructive interference, and that will look like a low watermark. And then I'll get all the stuff in between. But as I look along the wall, I should see sections with high watermarks, low watermarks, high watermarks, low watermarks, and so on and so forth. And it's because of this interference that's happening because waves superpose, right? Superposition just says that the waves propagating through the same medium at the same time, add together at every point, and how they do so then is called the interference. So this is sort of a real-world picture of the graphs that I was trying to draw on the board, right? The graphs that I was trying to draw on the board look a lot like this, except I had 2 slits. The size of the width is going to change the way the wave is affected. What we're finding out today, because I'm telling you, if we have waves incident upon a barrier with some slits in it, the size of the slit is important, but it's important relative to the wavelength of the wave. If we have a slit that's too small, it's very small in comparison to the wavelength. Basically, the wave can't even see that there's an opening. It just bounces off, right? If we have a slit that's too big compared to the wavelength, the wave just goes through without much deflection. This is really nicely illustrated by your microwave oven, right? In the front glass of your microwave is a screen that has some holes in it. These, they're not big holes in comparison to our size, but they're big enough for you to see through. So think about what that means. Visible light passes through those holes with no problem. That's why you can see into your microwave, right? What I'm saying is the size of the hole is large compared to the wavelength of visible light, so the light just passes right through. But why are they there in the first place? Well, it's because microwaves use microwave radiation. Microwave radiation has wavelengths that are longer than visible light. And it turns out they're on the same order as those holes, right? So for the microwaves, those holes are actually, not same order. Microwave wavelengths are actually much larger than those holes. So the wave can't get through those holes, it just bounces off. So from the perspective of a microwave, that sheet with the holes in it is like a mirror, right? It just bounces off. But for visible light, it gets right through. It's important because microwave radiation, you might know how microwaves heat up food. What's the mechanism going on there? Microwaves are actually very low energy, right? They're way lower than infrared rays. Why are they dangerous? Why can they heat up your food? Water molecules have resonant frequencies in the microwave range. So when you put microwaves incident upon water molecules, the water molecules start to vibrate, just like a wine glass vibrates when you thump it, right? Ding! That's what the water molecule does when you put microwaves on it. So vibration is energy, right? That's kinetic energy. So the microwaves are very low energy, but they deliver that energy to the water molecules in your food. That's how it heats it, right? It's different than normal cooking, which uses infrared radiation. It's actually a different set of chemical reactions. That's a different class. But it's important because you need to look into your microwave to see if your food is ready. But your eye is mostly water, right? So if the microwave radiation was able to get out, it would boil away your vitreous humor, usually considered to be a bad day, right? So that's why that screen is important. The holes are small compared to the microwave radiation, so it just bounces off of it. The holes are large compared to visible light, so it just passes right through it. If we find a situation in which those holes are on the same order as the wavelength of the light that's incident, you get stuff like this, right? You get this diffraction where a lot of the wave is reflected, but from the slit, some of the wave is allowed to get through, and you get the diffraction on the other side. So that's our stipulation. We're going to need the slit width to be on the same order as the wavelength of the light that we're putting on it, or any wave, but we're talking about light specifically. All right, now, subcontract out more graphics. So what we said last time was that the reason we get interference from waves is because the waves are taking different path lengths to get to a certain point. So you have two slits which are now operating as independent wave manufacturers, right? Because a wave is coming through each of those slits and spreading out independently. So when where are the graphics? I think it's here actually. Yeah. Nah, it's actually not what I'm looking for. They keep changing the book. But it's one of the disadvantages with electronic textbooks is they update them constantly. So I tend to lose things that I used to know where they were, but that's okay. Let's see what's right here. Oh, come on. This is annoying because I know the exact graphic that I want to get to, and I don't see it. Maybe it's here. Okay, so here's our situation. We have, this is a multi-slit system. You have 3 slits. We're talking about a double slit system. We'll talk about multi-slits also. But here's what's happening. What we've done is picked out one particular ray that's coming from these slits. Now, there are lots of rays, right? We drew that last time. There are rays all around. They're just not showing all of them. They're just showing one particular ray. Furthermore, they're showing the rays that are going basically parallel, right? If that's the case, we can just do the geometry here. So the distance between the slits is some d. That means the path length difference. If this ray is propagating to some area over here, and this ray is propagating to some point over here, the difference in the path length between these 2 rays is going to be this distance right here, where you can get just from the geometry as d sine theta. So that's important, hang on to that. The difference in path length between these 2 rays, when they get to their final destination, is d sine theta, where theta is the angle that this ray makes with the horizontal, which is our reference angle, and d is the distance between the slits, right? So, why is the path length important? Well, remember, what we said last time is if I move one of the sources back by a full wavelength, right, I create complete, or I just make constructive interference. If I move it back by half of a wavelength, I make destructive interference, right? What I do then is that if my waves are in phase at the first, I've got a peak lining up with the peak, and then if I move one half a wavelength, I've lined up the peak of one with the trough of the other, and that cancels. If I move it a full wavelength, well then I wind up lining back up the peaks again. So the path length difference is what makes the difference here, whether I get constructive or destructive. Full integer multiples of the wavelength, as in 1 lambda, 2 lambda, 3 lambda, 4 lambda, constructive. Half integer multiples, half lambda, 3 halves lambda, 5 halves lambda, is destructive. So what that means is that d sine theta is equal to an integer multiple of the wavelength, I get constructive interference. If d sine theta is equal to a half integer multiple, I get destructive interference. Okay? So here's that kind of, with the 3 slits, that's illustrated here. Here's d sine theta, that's 1 integer multiple difference. 2 d sine theta, that's 2 integer multiples. Alright, so also I'm going to ask you to make a slight approximation. Because what we're doing, let me just what's happening on the board. If this is my barrier, and these are the slits, and this is my detector. Again, if it's water waves, it might be a concrete wall where I can see the watermarks. If it's electromagnetic waves, it might be a phosphorescent screen that's going to light up when a wave hits it. So I'm going to say that if I pick out one point, right there, just point at random, there's going to be a wave from here that takes this path, and a wave from here that takes this path. And that path length difference is what makes a difference. Now, you can all see that these 2 lines are not parallel. This is where the scale gets in the way. But these lines are. What's going on there? Well, it's approximation, right? The deal is, this distance, d, is really small if we're talking about visible light. Really small. This distance might not be huge, but compared to d, it is really huge. What we're saying is, as long as this is some distance L, right? The distance from my slit barrier to my detector screen. If L is much, much bigger than D, we can model those as parallel. Right? Here's what I mean. If I come up, so I got these 2 guys, right? Jaron and is it Preston? Pierce, there was a P in there somewhere, right? If I'm right here, right, really close to these guys, and I point at both of them, my arms are making a reasonably large angle, right? I'm really close to them. As I go back here, though, and I point at them, you see the angle has gotten a lot smaller. Now, if I were to go a mile that way, you would not be able to tell at all that I had an angle between my arms when I pointed at them, right? So the farther away I get from these guys, the more I can say that my arms are parallel, right? Are they parallel? No. I would never be pointing at both of them individually if they were. But for all practical purposes, as long as L that's L from me to them is bigger than D, which is the distance between those two guys. As long as it's much, much bigger, I can say it's practically parallel. That's what's going on here. If it was parallel, they would never get to the same point, but it's basically parallel. Okay, so that's the approximation we're going to make. Once I make that approximation, I can now say this. If d sine theta, which remember, that's the line with which I'm going to measure theta. And for both of those lines, as long as they're basically parallel, theta will be the same. If d sine theta equals m lambda for m equal to 0, 1, 2, etc., integer multiples. If that's the case, then this is a bright spot. This is constructive interference. Right? I'll put point P. P is a bright spot. Okay? In other words, if the path length difference is equal to lambda or 2 lambda or 3 lambda or even 0 lambda, it's not, but it could be, right? Then that's a bright spot. That's where I get constructive interference. But if d sine theta is equal to a half integer multiple of lambda, here's how I'm going to write that for reasons which will be clear in a second. M plus 1/2 lambda for m equal to 0, 1, 2. P is dark. You get complete destructive interference if that's the case. Any questions about that? Alright. The reason I write it like this is because I want to be able to use the same m's for both of these. So here's how it works out. D sine theta is equal to m lambda or m plus 1/2 lambda. This is constructive interference. That is bright spots. This is destructive interference. That is dark spots. For m equal to 0, I'm going to say plus or minus 1, plus or minus 2, plus or minus 3, etc., etc. We'll talk about the pluses and minuses in just a second. Let's see what that gets us. If m is equal to 0, what do I get here? Well, I get 0, which means theta, or it means one of these is 0. My candidate is the sine of theta is 0. If that's the case, then theta is 0. Well, how do I interpret that? Well, if this is my detector screen, and this is where my slits are, there's an angle of 0, right? It means we've got a bright spot right here. Alright, go to the next m. That takes care of 0. We'll forget the negatives for now. Positive 1. Well, that means the next, well, if this is positive 1, that means d sine theta is equal to lambda, right? Not 0. Lambda is the wavelength of the light, which means I have some positive angle at which I find another bright spot. That's going to be maybe right here. Where this angle now is whatever I'm putting in for theta here. It's another angle. Okay, keep on going. M is equal to 2. Well, it's going to give me another d sine theta is equal to 2 lambda. That means theta is some bigger positive angle, which means I've got another bright spot right here. So this corresponds to m is equal to 0, m is equal to 1, m is equal to 2, and so on and so forth. You see how that works out?